Good afternoon, ladies and gentlemen, and welcome to our panel titled Nuclear Power, a Sustainable Clean Power Source. I'm Kemal Pasha Mehmetoğlu. I'm from Idaho National Laboratory, and I have the honor of moderating the panel today. We have a number of distinguished panelists, and I'm going to introduce them in a while. But before we start with our panelists, we are also very fortunate to have a very special guest as the keynote speaker for our panel, Dr. Ernie Moniz, the Secretary of Energy in the United States. Dr. Moniz doesn't really need a lot of introduction. He's been a leader in the energy field as well as nuclear energy field for a long time. He currently serves as the Secretary of Energy in the U.S. administration. He implements the critical energy missions at the Department of Energy, encompasses advancing the President's all of the above energy policy, maintaining the nuclear deterrent and reducing the nuclear danger, promoting American leadership in science and clean energy technologies, as well as cleaning up the legacy of Cold War. Prior to his appointment in the administration, Dr. Moniz was the Cecil and Ida Green Professor of Physics and Engineering Systems at Massachusetts Institute of Technology, MIT, where he was a faculty member since 1973. Without any further ado, I would like to introduce Dr. Ernest Moniz.
Well, thank you, Kemal, and also greetings to the panelists. I'm really pleased to have the chance to come here to the COP and have a chance to discuss nuclear energy, nuclear power, as one of the essential elements of the low-carbon portfolios, certainly not everywhere, but I think in many parts of the world, and I'm certainly hoping as well in the United States in terms of a continuing major contribution to low carbon. Here in Paris for this COP meeting, where obviously a critical negotiation is going on for setting the pathway to a very low carbon future. I think it's important to remember that as we look at solutions for climate change, for mitigating the risks acceptably, I think there are two elements that are certainly common to just about every reasonable modeling of that future. One is there clearly has to be a very significant demand-side contribution, energy efficiency, conservation, and the like. Behavioral change may be a part of it, but certainly we will have to have very strong demand-side contributions. But secondly, as we go to a low-carbon future, just about any, again, modeling of that future has decarbonization of the electricity sector as kind of a leading element. In electricity, we have a lot of options. We have stationary sources. We all know the reasons why, in fact, those are kind of two common elements in a low-carbon future. Then if we talk about a decarbonized or a largely decarbonized electricity sector, obviously nuclear is, and I think many of us think must be in the future, one of the main contributors to that portfolio, where the options are fundamentally renewables, nuclear, and carbon capture. So I think nuclear is very important. Now, as we, in my brief remarks today, I want to talk in terms of kind of a few time scales. In terms of the nuclear issues that we address for deployment in those timescales, although I want to emphasize action is required on all elements of the program now and in the near term. Certainly, when I think of timescales, we all can, I guess, choose our favorite demarcation time, I will say 2030 stands out to me for a number of reasons. First, a critical feature of this COP meeting is the fact that we, the world, came into this meeting with INDCs, with national targets for almost every country of the world, and most of those are in a kind of a 2030 time frame in terms of targets. So that's an important point. We can discuss what comes after 2030, of course, but 2030 is where I think the targets being set today typically have a time horizon. Secondly, if we go to the United States, in many ways, well, certainly a very central element of the President's Climate Action Plan is the Clean Power Plan. And that, again, has a kind of a 2030 time frame where a 32% reduction is the target in the Clean Power Plan. And finally, if we go to the nuclear enterprise, if we take 60 years as a typical lifetime for a reactor. Now, we'll talk about, of course, the possibility of an even further extension, but we know already that 60 years is a very, very, very credible. In fact, we are seeing it in front of us in terms of licensing of reactors for 60 years. Well, then, simple arithmetic and the schedule of building reactors tells you that 2030 would be the time then to start a very substantial wave of retirements at a 60-year mark. And so, once again, it's a very important time period. Either we will have another life extension period for the majority of the fleet, or we're going to be in the business of replacing a lot of carbon-free power at that time frame. So again, that kind of gives me a little bit of a reference frame, at least in terms of how I think about it, and remembering that in the carbon discussion, once we at 2030, maybe we can take a little bit we can exhale and then get right back to the job of even more stringent requirements as we go forward in terms of decarbonization. So in that context, I kind of think of maybe a near-term and then an intermediate term up to 2030, and then a longer term. Certainly in the near term, a critical issue that we are facing is that of maintaining the existing fleet, where I'm not talking about pressures from reaching 60 years. I'm talking about pressures from natural gas prices and other issues in the marketplace. Just as a reference, numerical reference, a retirement of roughly a third of our nuclear power plants is the equivalent of about 100 million tons of CO2 per year. So gives you a scale that if we have retirements that are significantly beyond those we're seeing already, we have a big carbon hit, and that's even assuming natural gas as the primary replacement for nuclear power. So clearly, the issue of the operation of current plants is very important. As we think ahead to the medium term and 2030, I think that it is critical that the utilities understand with sufficient lead time before 2030 what they can include in their capital plans for meeting the 2030 and beyond. And so that means maybe we have 10 years, that's a little bit optimistic, to really establish a set of options for going forward. So that would certainly include the issues of completing and understanding what's happening with our current advanced generation 3 plus, let's call it, of reactors, where we have 4 being built. In the United States, we have quite a few more being built in China, and understanding cost and schedule performance and where we can go with those as we build more of those is going to be very critical for decisions to be made. We also, certainly in the United States, but in many other countries, we really need to understand, in my view, we need to understand the performance of small modular reactors. I mean, I'm talking now about those based upon light water technology in the sense of getting one or more. I know we will have a discussion on the panel of NuScale in particular, heading towards design certification submission to the NRC next year, and we need to start seeing, real things happening early in the next decade if we're going to have that set of options available on the time scale that I mentioned. I should say in both of these time scales, including the short one, another very important issue. It's relevant to the continuation of our current fleet. It's also relevant to the decisions that are going to be taken in terms of future capacity additions as to how our electricity markets are or are not restructured. We know that for example, all the services in the electricity system are not valued in a very sophisticated way, shall we say, and some of the important features of nuclear power, other sources as well, demand side programs as well. We just need to get to a better valuation system, and I think that will be important for nuclear power in particular, and certainly important for investment decisions that will be taken. Then there's a longer term where clearly we have to be investing in, I think, advanced concepts. We have to be investing in developing the infrastructure needed to think about advanced concepts in the United States. So lots of decisions in the relatively near term in terms of how we structure our portfolio for addressing these longer term issues. So I'll just say a few words about some of these points and leave it to the professionals on the panel to go into more detail. If there's time, I might just say a few words at the end in terms of the nuclear spent fuel, nuclear waste issue. So I said it already, but let me repeat something on this question of, in the near term, understanding and evolving market structures. In April of this year, we published the first installment of the Quadrennial Energy Review. That was looking at energy infrastructure. Of particular relevance here today, I would say, is that our second major installment, which is underway, is on the electricity system as a whole. From end to end, from supply through demand side, and in that, what I want to say is right up front, we are very actively looking at this question of valuation, which we think is really central to how various supply, low carbon supply, is going to come into the system. So just want to say that is a special focal point right now in our energy policy work. How the Clean Power Plan implementation plans evolve in the states is going to be very important in terms of the incentive structures for existing plants. In my view, there's no matter how the Clean Power Plan goals were set, the implementation plans are going to have to look at the reality of nuclear power as low carbon source. So that will be very important, and I invite you all to talk to Gina McCarthy, who is here as well today, in terms of how they're seeing this happen. I might say that the Department of Energy is working in terms of a technical assistance mode, if you like, with states in order to help, in a technical sense, the development of SIPs, of the state implementation plans. In terms of moving forward, one of the things that we are doing as well is we have a light water reactor sustainability program with research in partnership with the NRC and the industry to address aging materials, obsolescence of residual analog technologies, advanced safety analysis, a whole set of issues there, which we think, again, are important components of the question of addressing whether or not further life extensions, for example, will be in the cards. We also have a few years ago, 2010, DOE started a set of innovation hubs. The very first hub was in nuclear energy, Castle at Oak Ridge, developing large-scale simulation tools for the analysis of nuclear power plants and fuels, and that's been very, very successful. Another tool that I believe will be very helpful in looking at the safety and life extension questions. In fact, accident-tolerant fuels is another major focus in our program going forward. Fuels that address things like hydrogen buildup, et cetera. Obviously, Fukushima, the Fukushima accident has put, I think, a premium in terms of this kind of research program. The issue, okay, nuclear waste. I'll come back to nuclear waste a bit later. I think I'll leave that for the moment. Going to the modular reactors. Again, I'm not going to say too much because I know in the panel we'll have a discussion. But I just want to say that we remain very bullish, certainly on the imperative of advancing small modular reactors to the point where we can really all understand not just their technical performance, and we certainly see these reactors as having excellent characteristics, safety characteristics, et cetera. But let's face it, we are going to have to understand what is the real world financial performance of these reactors, and especially to understand what will be the economies of scale as one goes to a scale-up of the deployment of these technologies. So that's something that I think we still have to work on, the scale-up part. But the first thing is to get the first group out there, and then we'll have to look at the scale-up. But I want to emphasize again what I view as the urgency of moving on this, because I think we need to have this option on the table, understood on the table, as those mid-decade, next decade decisions are going to be made for capital planning. In terms of the longer term, I think I think we need to, and I'm pleased to see that I think we are lifting our headlights a little bit in returning to looking at more innovative concepts as well in the nuclear arena. Now, one generic initiative about which we are tremendously excited is the one that was discussed here last Monday by President Obama and the leaders and senior government officials from 19 other countries, the Mission Innovation Initiative, in which the 20 countries, which collectively currently have, I would call it a quasi-public R&D budget, energy R&D budget of about $10 billion, those countries committing to a doubling of that over 5 years. So adding another, say, 5 years from now, adding another $10 billion to the base of energy R&D annually, we believe will obviously open up the innovation pipeline and give us many more opportunities for that longer-term impact where we're going to have to crank down very, very strongly on carbon, including, as I said earlier, essentially more or less decarbonize the electricity sector. The mission innovation announcement, I don't know how familiar everyone is, was accompanied by a parallel announcement of a private investor network put together mainly under the leadership of Bill Gates, in which investors from 10 countries are going to put billions of dollars on the table with the idea of investing with much more patience than is typical and with much greater risk tolerance than is typical. And so the idea is that they will be looking to invest in the products of this expanded innovation pipeline in the mission innovation countries. Now, nuclear has to be part of that. It's interesting that, of course, Bill Gates certainly showed that characteristic of investing with patience and risk tolerance in investing in TerraPower as one example of a much more step-out nuclear technology. And in the United States today, we have almost 50 companies with private funding looking at novel nuclear concepts, both fission and fusion. And I think this is, again, another direction that we need to go in. And with mission innovation, again, I at least feel very strongly that we need to see nuclear as part of that portfolio based upon very, very promising concepts. In terms of supporting private sector progress on nuclear, we announced last month the Gateway for Accelerated Innovation in Nuclear, or GAIN. And Kemal, where did he go? He's oh, you're there. I think is the director, I believe, of GAIN out at the Idaho laboratory. And the idea here is to provide the industry with access to technical, regulatory, and financial support to help commercialize new and advanced nuclear reactor designs. I think this is an important job for our national laboratories, and one that can only be carried out successfully, however, in collaboration with universities and the industry. Certainly looking at, again, ideas beyond light water reactor technology that may be important further down the road. So that's just kind of a, hopefully at least gives you an idea as to how I at least am looking at how the nuclear is fitting into the bigger puzzle in terms of a low carbon future, its importance. Maybe I will just add a word on the back end side, and to say that we will continue to advance what is fundamentally the set of recommendations made by the Blue Ribbon Commission a few years ago and endorsed by the administration, and that means that we will be advancing our consent-based processes, both for consolidated storage and for disposal. And on the disposal side, many of you may have noticed in the summer, the President issued a determination that we also now have the flexibility of pursuing defense waste and nuclear power plant spent fuel disposal on separate tracks, which I think is going to be to the benefit of both tracks, in fact. So just want to say that in 2016, I expect that we will be moving out in this direction as well to address the back end challenges. So with that, I'm going to conclude. Again, I think that I've laid out kind of these three different sets of challenges over different timescales, but I want to end by repeating that the work on all of them has to go on now as we address these challenges for this decade, the next decade, and the longer-term future. So thank you very much, and I'm sure you're going to have a very stimulating rest of the session. Thank you.
Thank you, Dr. Moniz. For those of us who are looking at nuclear energy as part of the climate solution, certainly these are very good news, exciting news as we look forward. Now what I'm going to do is introduce each panelist. And after I introduce the first panelist, I'll let the panelists speak roughly 5 minutes, make some opening comments about their specific technology or their specific perspective on the nuclear energy. When we finish all 4 panelists, after that, we will go into a question and answer and discussion session. So our first panelist, starting from left to right, our first panelist is John Hopkins, Chairman and Chief Executive Officer of NuScale Power. John has been in that position for about since about 2012. Prior to joining the NuScale, he held numerous executive positions in his 24 years of service with Fluor Corporation, which is a Fortune 500 international engineering and construction company. He had many positions in Fluor during those 24 years. In addition, he's very active professionally and in civic organizations. He's serving as the Vice Chairman of the United States Chamber of Commerce in Washington, D.C., a member of the Nuclear Energy Institute Board of Directors, and a Senior Policy Advisor for I-Squared Capital, New York. The floor is yours, John.
Thank you, Kimmel. If I could just pick up where the Secretary of Energy left off, the NuScale Power mission is very simple. Well, not very simple, but it's to bring affordable, scalable, and mass deployable clean energy to the world. What you have behind you, and I was asked to be able to show you one slide, is if over you look in the fore corner, that's the NuScale Power module. It's a 60 megawatt thermal. The dimensions are 22 meters tall, and that includes containment, 4.5 meters wide. We currently have close to 700 people working on this project today, and we're also seeing a lot of attention beyond just the United States, but also elsewhere. We've recently opened an office in London, in fact. We have 200 patents pending, awards, and we're in patents in 20 countries. The module itself can incrementally be installed one at a time, up to 12 modules. And so at the 12 module level, you can have 600 megawatts. Within the US, we see our sweet spot is for coal replacement. In fact, our first customer, Secretary Moniz said that we are in the process of submitting our design application to the NRC. We will do that 2016. And then we have a commitment for coal replacement in the US, even with natural gas prices being where they are today, to be commercially viable and operational first quarter of 2024. You ask why 2024? We still have to go through the Nuclear Regulatory Commission gold stamp. We have 3 major imperatives. One is global needs, one is customer needs, and one is market needs. What we see today, there's 1.3 billion people without electricity. We strongly believe that these small modular reactors can be used either by dry cooling or wet cooling in areas of the world that either have no grids or small grids. And we also are not looking to compete against large reactors. We're not looking to compete against clean energy technologies such as renewables. We actually see ourselves with the ability to complement these. In dealing with the market segment, what I have put up here, we recently had 5 studies, actually 4 studies committed to last year. One is, do we have the capacity to complement clean energy technologies such as wind? We've done a lot of testing on this, and we have the ability, because we have the opportunity within each of these modules as dispatchable to scale up and scale down to help complement intermittent power. We're also working with the Idaho National Lab right now for hydrogen production. As you know, hydrogen production is in the formation of synthetic fuels. We also have even looked at it from a fossil fuel side, by able to provide steam requirements, central heat to oil refineries who are now using fossil fuels to provide their own energy requirements. Can you imagine if you have a small modular reactor that has no CO2 emissions providing the needs of an oil refinery? And then last is, and I'm a big believer in this, is the area of desalination. If you were to take eight of these modules, it could provide enough electricity and water to sustain over 300,000 people in the world, in a city. And the last one I'd like to just to mention, we've had numerous conversations about cities of the future. What is going to be the energy requirements for cities of the future? I mentioned the scalability of these units. So you don't have to have 12 units up and running. You could put 2 units in, you could provide power and generate revenue to offset the cost of the next unit and the next unit. And also, as the population density of these cities grow, you can scale up to meet the needs. So we're bullish on this. Something that was said that's critically important is commercial viability and affordability. Nuclear's not done a good job historically in being able to meet. They generally overschedule and underachieve when it comes to cost and schedule. The reason people say, why are you at 50 megawatts? That was the envelope of size that we felt comfortable that we could actually build these, not only the reactor, but the containment in a factory, because they have to be able to be designed where they're commercially available and deployable in a means that we can get them around the world. So right now, our customer looked at their overnight costs for the first of a kind. We have a customer. As I said, we're committed, and our costs are complementary to what fossil fuels are today. Thank you.
Very good. Thank you, John. Our next panelist is Jeff Harper, Executive Director for Strategy and Business Development in X Energy. Jeff brings 30 years of entrepreneurial, general management, and nuclear power experience, almost all over the world, Africa, Europe, and USA. Before X Energy, he worked in Westinghouse Advanced Reactors Program, Pebble Bed Reactor. He also worked on small modular light water reactor technologies. He managed licensing activities for AP1000 reactors in South Africa, Czech Republic, Brazil, and Italy. Prior to Westinghouse experience, Jeff was the founder and CEO for Turner Harper and Associates. Along all those, Jeff also served as a vendor inspector for U.S. Nuclear Regulatory Commission, where he has led 30 management, technical, and quality assurance inspections. So Jeff brings a wide variety of nuclear experience in a wide variety of technologies. So the floor is yours, Jeff.
Thanks a lot. I'd like to also thank DOE for the platform here, as well as for supporting advanced nuclear reactors through some of their policies, especially GAIN. So we'd like to thank you for that. I think history will record that this conference has been a real milestone for clean energy, namely the agreement among countries on climate change, what the Secretary mentioned, mission, innovation, announcement, and also Bill Gates and the other billionaires that basically announced this energy coalition. I mean, it's very exciting, actually, and the ultimate when it comes to social entrepreneurialism. Our founder, Cam Graffarian, X Energy founder and CEO and principal investor, he is basically part of this social entrepreneurial movement. So since 2010, he basically launched this company, and our product is the XC100. As you see here on the slide, it's a gas-cooled reactor, the gas being helium, the fuel being pebbles. So at 50 megawatts electric, we'll sell these in 4-packs, so you're looking at a 200 megawatt electric machine. We're really innovators of this technology. Actually, it's a very mature technology. In fact, the Germans have 30 plus years of experience with this technology through the AVR, THTR, and HCR Mogul. Then the Chinese took where they left off, and they actually have a prototype that was actually launched full power in January 2003, and that would be the HTR-10. The Chinese are now actively pursuing commercial markets with their HTR-PM. They're looking at 12 plants, and the first plant that they're putting up started construction in 2012. They're looking at finishing in 2017. So we're really innovators. We're trying to bring this technology to market in the U.S. And in fact, DOE in 2014, in their technical review committee said that, X-Energy pebble bed concept has the greatest readiness for licensing than other technologies or other reactor concepts. So our fuel, again, is a pebble. So as you can see, hopefully you can see this, but it's the size of a billiard ball, pretty much. But it packs a lot of energy. So this pebble, if you can imagine, our pebble would be like 8.5 metric tons of coal. That's significant. And with that 8.5 metric tons of coal, you're looking at an equivalent of 27 metric tons of ash. So truly, this is a phenomenal technology, and we're all excited about it. DOE has done a lot of work with TRISO fuel, which is part of this, the makeup of this technology, this pebble bed technology. We can burn uranium, we can burn plutonium, we can burn thorium, which makes it very flexible. Lastly, let me just say, in terms of light water reactors, large light water conventional reactors, let's put it that way. Safety, if you compare with the advanced high temperature gas reactor, on the safety side, our reactor is meltdown proof. And I say that because of the materials we're using, graphite, also low power density, and also negative temperature coefficient. All those work together to make it meltdown proof. The other thing is water conservation. We're using gas, helium, as opposed to large amounts of water for cooling. And we use also, as John mentioned, they could do with dry cooling as well. Distributed power. So as opposed to having to have an infrastructure of large grids, we basically would operate in a microgrid environment. And I think the last thing that's on a high level would be just the time of construction. We're looking at a much simpler configuration. Conventional nuclear is taking anywhere from 6 to 10 years. For construction time, we're looking at 2 to 3 years of construction time, along with selling these units in chunks, in smaller chunks, as opposed to 1,000 megawatts electric. We'll be selling them at 200 megawatts electric, and they can scale up.
Thank you, Jeff. Our next panelist is Donald Wolf, the founder and executive chairman of the board for Advanced Reactor Concepts, shortly known as ARC. Mr. Wolf is the founding shareholder for ARC. He's an business executive and a venture capitalist who had senior level founder responsibilities in many different businesses. He's the founder of Société Tigre Sarl in France and European Property Partners in US. He has done a lot of work in real estate. His firm has funded and closed many hundreds of millions of dollars of property transactions internationally. Prior to funding Tigre and EPP venture, Donald was the general partner in the Holloway Group, a real estate development company, a major real estate development company in the Mid-Atlantic region. He began his career as an analyst in the systems analysis group of the Office of U.S. Secretary of Defense. With that, I'll turn the microphone over to Don.
Thank you. Hello? 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 Hello. Well, what's obvious is I'm in fairly deep cotton here among these true nuclear experts. I am an engineer, but not a nuclear engineer. I represent a company that is developing an advanced reactor that is cooled by liquid sodium, and its fuel is an alloy of uranium. Those two one is quite unique, the alloy of uranium. The liquid sodium is not so. The liquid sodium has been used by many countries. Our technology is derived from a U.S. government program, not from the Chinese or from the Germans, but this is a program that the U.S. taxpayers paid for. It was called the Experimental Breeder Reactor 2, and it ran for 30 years before it was shut down. And after that program, there was another program done by DOE that made it through about 1993, called the IFR program. And 3 members of my team were senior participants in the EBR2 program, and that 3 plus another were senior participants in the IFR program. And in fact, their desire to bring those programs back with the technology that was developed is a major motivator of our team. And let me tell you a little bit about what are the special features of this reactor. As I said, it's 100 megawatts electric, 260 megawatts of heat. The first thing you can say about it is that it is truly based on its internal physics. It has inherent passive safety. Doesn't require a piece of molten salt to melt. It doesn't require a lot of water. It doesn't require anything. What happens is, and I'll tell you, I want to go into this just very briefly without going into all the physics, but the reactor, when it starts to heat, the sodium starts to get warmer. And if you had, let's assume you had Fukushima, with all the electricity go off, no pumps to move the coolant. Coolant starts to rise. Well, the core is constructed in a way that it starts to expand. And as it expands, you have neutron leakage. That is, neutrons exit the core without being captured by another atom, an energy atom. At that point, the heating stops, and the reactor actually cools back down to the stable point where it started. And this is not just our speculation, it's not modeling. It was actually performed multiple times in the 80s, and you can look it up on the internet. It's called the stability performance of the EBR2. Number 2, because it's sodium cooled, sodium operates at the boiling point is 900 degrees centigrade, which is well above the 300 to 500 degree operating range of the reactor. What that means is the reactor operates at atmospheric pressure, and the pressure containment vessel is a thin wall stainless steel tank as opposed to a 6 to 12 inch forged steel containment vessel, which you have to get at least get water up that high. And that is a big simplification. The reactor is, as you can see in the picture, it's 50 feet tall, and way down in the bottom is the core, and the containment vessel is just a stainless steel tank. And there are no pipes that come out at the side for leaks. All the penetrations are through the top. And the sodium sits quietly down in the bottom and doesn't even bubble. What that allows is because of the inherent safety and the atmospheric pressure, the cost to construct, we project, is going to be substantially reduced. The nuclear island is about as simple as it can get. It's a reactor down in a pool of sodium. And all the secondary safety systems that really drive up the cost of light water reactors, and they are safe, but you have to have many multiple layers of safety systems. We don't have to have that. And we have a 20-year refueling cycle. We chose that. We put a lot of uranium into the reactor in the beginning, and we actually have we have cladding that's been tested almost to that full 20 years, and it stays in the reactor, and there's no refueling, which means that the reactor operator doesn't have to have experienced staff that refuels every 18, 24 months. You don't have to take fuel rods out and store them on site in a pool, such as with a problem at Fukushima. And you don't have to have the equipment to do the refueling, which is part of your upfront cost. At the end of 20 years, a team would come, and because the reactor operates at a low density of power, it takes about 2 weeks for the fuel rods to cool down enough to where they can be put in a dry cast and taken away for either storage or some additional whatever you want to do with it, which is the next thing. I think this reactor technology, and this is probably where it's unique, because it's a fast reactor, it opens all kinds of new doors to what to do with nuclear waste. And the fast reactor means that the medium through which neutrons pass are not slowed down. Water molecules have hydrogen atoms. They're the same atomic weight as a neutron. They slow down very dramatically the passage of a neutron. The sodium atom is 23 times as heavy as a hydrogen atom. So it's like a billiard ball hitting the cue ball hitting billiard balls or hitting a bowling ball. And so you have high energy neutrons. The result is that you get about 40% burnup of the fuel as opposed to 3 to 5%. Now, and the 60% that's left, and in fact the entire fuel core of this reactor at the end of 20 years can be taken out, the cladding, the stainless steel cladding removed from the fuel. You then melt it and put it right back into the next core. There virtually is no waste that has to go into the ground. After you do this a few times, there will be what are called fission products will have to come out, but they won't be a large percentage. And we believe, and we have a patent on this, that we can actually take light water waste and we can grind it up and melt it in with our fuel pins, and you can run that as well. So what you have here, think about it, you have a reactor that generates very little waste of its own and can actually burn and incinerate the waste of others and generate baseload power. Lastly, we have a couple of features of the reactor that we think make it a very, very effective barrier to proliferation. The first one is the 20-year refueling cycle. Think about it. The fuel comes in from an international source, goes inside the reactor core, where it sits 50 feet down inside of a pool of hot sodium. Sodium is not like water. You can't see it. So it is virtually impossible for a bomb maker to try to extract a fuel rod without the off-site equipment that we own, provide, and would deliver. So you have the fuel. There's no stored fuel on site. You don't have fuel rods that are moving in and out every 18 months with refueling. It comes on for 20 years, goes away for 20 years. The last thing I was going to say is I think my colleagues have the same feeling. I think that our reactor is fairly close to being licensable because of the 30 years of performance at the EBR-2. The operation of it is well documented. DOE has the documentation. We and others have been gathering the statistics that would be used in licensing. And I think if need be, we could meet the goals that were set by the Secretary. We could be licensed in 10 years, and we could be deployable in 5 bore. Thank you very much.
Thank you, Don. Our last panelist is Eugene Grechek. On this panel, he is representing the American Nuclear Society as the president. but he has also 40 years of hands-on experience for commercial nuclear power generation, including operations, engineering, licensing, training, security, and emergency planning. He has worked with Dominion Resources. He held positions like nuclear station manager, site vice president at a couple of different stations, and vice president over nuclear services and nuclear engineering. The floor is yours, Eugene.
Kamal? All right, yeah, here we go. Thank you, Kamal, and I really appreciate the opportunity to sit here. I'm glad that so many people have come in to hear about some really exciting things in new nuclear technology. As Kamal said, I'm here as president of the American Nuclear Society. The ANS represents about 10,000 of the professionals that are involved in all of the technologies that you've heard here. So we're not, as opposed to my other three esteemed panelists, I'm not here to sell a particular design, but we're really here to sell nuclear technology as a whole. And the role that the American Nuclear Society has played over the last 60 years in bringing nuclear to a commercial standpoint that it is today, and then also what it can do in the future. We've been very instrumental in providing the forum for where technical advances can be presented to scientists and academicians' peers, as well as very active in the standard-setting organizations that establish the basis for many of the regulations that apply to the existing generation of nuclear power stations, and we would expect that they would apply to future technologies as well. You know, we've heard some really exciting things here about new technology, and I'll talk about that in a moment, but I really need to start with a reiteration of something that the Secretary said, and that is how important it is for the existing generation of nuclear power stations in the world and in the United States to remain in operation. As you probably know, some of the plants in the United States are facing some economic challenges that are largely due to market distortions that currently exist, and also due to the fact that their contribution to a carbon-free electrical economy are not really recognized by the short-term electrical markets that currently exist. So some of those plants are economically challenged, but every time one of those plants shuts down, the replacement for that power is going to be additional carbon emissions. So here at COP, we're having discussions about what the future looks like in terms of what future energy supply can do to reduce carbon emissions, and yet we face a very real situation on a day-to-day basis about the existing carbon-free generation being economically challenged, and that's something that we really need to work to address. Nuclear supplies about 2/3 of the non-CO2 emission electricity in the United States today, and so therefore it's extremely important that that stays in operation. Now, as far as new technology, think about it. There is no other technology in the world that we would expect to be essentially static for 50 or 60 years and to still be competitive either technically or economically. And the current light water reactor technology that's used throughout the world has done very well. Utility companies have learned how to operate these plants with greater than 90% capacity factors. They are online 24/7, 365 days a year, come down once every 18 months or 2 years for very short time for refueling. They are the base load power that we all depend on. But they are essentially based on technology and design concepts that were introduced and perfected 50 or 60 years ago. And if you think about anything else, whether it's consumer electronics, whether it's even automobiles, vehicles, there's so many examples of how technology has advanced through research and through innovation. And largely, the nuclear enterprise has not had that opportunity for a long time. And that's what is so exciting about some of the opportunities we've heard about how we can make that advance. So we base on 50 years of operating experience, but we're also looking at being able to solve many of the problems that people traditionally just associate with nuclear and in some cases take it for granted. ANS has been here as part of a Nuclear for Climate initiative. It's 140 technical associations around the world that got together to say, at this COP, it's important that people understand the vital part that nuclear can play. And so our booth is over on the other side of the room. We've had people coming to us and saying, what are you doing here? This is an environmental conference. Why is nuclear here? And after we explain it to them, some people come away and say, okay, now I understand. Others have this deeply embedded, what I would consider irrational fear of nuclear. And I think all of us have a challenge to how to take the exciting prospects that nuclear can play, not only exciting, but necessary, that it needs to play, and to get over some of these irrational, almost inherent to, I don't need to discuss the facts, I just know why I'm opposed to nuclear power. So I think we've made a difference here. I think we see a real understanding of the importance that nuclear has to play, and I look forward to answering any questions on that regard. Thanks.
Thank you, Jean. Okay, in order to provide sufficient time for Dr. Holden to make his closing remarks, I think we only have time for just one question for all the panelists, and I'd like you to answer it in 1 minute, please. And it is 1 minute per panelist, not 1 minute total. And since I only get to choose one question, I'm going to make it self-serving. Since I'm the director of GAIN, I want to get your feedback on GAIN. I'm sure you've heard about GAIN, Gateway to Accelerating Innovation in Nuclear. And you represent different types of technologies, and you're looking at different time scales at different maturity levels. So from your perspective, starting with John, from your perspective, what is the most important thing that GAIN can do for your company to be successful?
Thank you. Actually, I think right now for us, there's 3 areas. Technology maturation. If you look at the continuum of where we are in our process, we're moving into proof of operations. And with the experience of the labs of knowledgeable and experienced people, it can be of tremendous help to us. Secondly, in the program as it relates to land, and the ability to, we have a customer, we're committed to the customer is looking at siting operations right now. One of them is looking at the Idaho National Lab in Idaho, where you have the site characterizations done, the permitting's done, and the local community and lab is very receptive in our customer looking at perhaps siting their first 12-pack at the lab itself. And then the third one, codes and testing. It's an incredible amount of computer time it takes for us to do when it relates to codes and texting. If we had access to the lab's supercomputers, it could move us along that much quicker. Thank you.
Thank you, John. Same question for you, Jeff.
Well, like John, we're really concerned about the NRC, and because high temperature gas, specifically pebble bed, has never been licensed by the NRC, whereas LWRs have been. So that's one area that we would love to have help in. I think the other one is financial. The small business vouchers, that's very interesting to us, and we hope that continues on, as well as the loan guarantee program. I think the loan guarantee program, there may be some things that we can talk about. For example, your fees to get involved. It's $350K, I think, non-refundable fee, application fee, I believe, and also there's a large annual fee. So that's something that an entrepreneurial company would struggle with, I think. And lastly, on the technical side, ours is pretty much fuel qualification for the licensing. So, I know there's a lot of work that's been done at the labs, and hopefully that will continue, as well as there's not been any manufacturing capability, or there's not any manufacturing capabilities for the pebbles in the United States. So that's something else that we may take a look at.
Thank you, Jeff. Same question for you, Don.
Kamal, I think the main thing we could get from your program is assistance with licensing. And what the uncertainty about licensing means is it makes it very difficult to find financing. You're faced with a very uncertain future. You spend $200-300 million getting your plans ready, submit them into the NRC, and 4 or 5 years later you find out whether you've got a go or no go, and in the interim you spend another $100 million. Some of the other countries, the UK and Canada in particular, have a series of milestones that give an investor confidence that you're making your way down a road that is going to lead to a license. That would be a big step. I know there's been some discussion of that in the workshop we attended in the fall between the NRC and DOE. That would be a big help. Clearly, anything that could be done to make the licensing process more certain for a new technology. Same as my issue, same as Jeff, primarily.
Thank you, Don. Well, Eugene, since you're representing ANS, I'm going to slightly change the question for you. GAIN is supposed to be a gateway between the national laboratories infrastructure, the research infrastructure, including universities, and the private sector. As a national institution, as ANS, what can ANS do to make GAIN successful?
Yeah, thanks, Kamal. You know, I think as we mentioned before, there is a need to be able to take the concepts that are being developed here and to put them into terms that the public can fully understand the benefits of nuclear. And so, you know, each of the technologies that you've heard here were based or are based largely on research that was done many years ago in DOE establishments. And I think there are opportunities by entrepreneurs out there today in our educational institutions that are coming up with ideas that are even better than that. And yet they really need the opportunity to get that same kind of access to laboratory work. And then we can take that information and present it to the public. What's something we've seen here this week is there's a tremendous amount of misunderstanding about fundamental nuclear concepts, and when people misunderstand, that vacuum is filled by fear in many cases or misinformation. So the more information that's available, the more that we can actually put it into terms that the public can understand, and then not be afraid to actually talk about it in a public forum, not to be afraid to come to an environmental conference and say, this is why nuclear is important. So I think it's important to get the technical information put together, package it in such a way that people can understand, and then we need throughout our educational and public outreach systems to make that information available, that people understand how important and desirable this is.
Thank you, Eugene. Before we go to our closing speakers, I want to give another round of applause to all the participants. And Dr. John Holden will close out the session. John Holden is the White House Office of Science and Technology Policy member. Prior to joining the Obama administration, Dr. Holden was Teresa and John Heinz Professor of Environmental Policy and Director of the Program on Science, Technology, and Public Policy at Harvard University's Kennedy School of Government, as well as a professor in Harvard's Department of Earth and Planetary Sciences and Director of the independent nonprofit Woods Hole Research Center. Previously, he was also on the faculty of the University of California, Berkeley. Dr. Holden, the floor is yours.
Kamal, appreciate that and appreciate everybody being here. It really is a pleasure for me to be here and to follow Secretary Moniz and this distinguished panel to talk about the important role that nuclear energy currently plays and the even bigger role that it can play in helping this country and the world meet their energy security and climate change mitigation goals. As I think everybody in this room is aware, President Obama, whom I have the pleasure of serving as his chief science advisor, considers addressing the global climate change challenge as one of his top priorities. The challenge of acting in time and ultimately acting adequately is daunting both for the United States and for the world. As Secretary Moniz has said, in the United States, the electric power sector is the biggest emitter of greenhouse gases among all the sectors. It's bigger than transportation, bigger than agriculture, bigger than non-electric uses of energy in industry, and bigger than non-electric uses of energy in residential and commercial buildings. But achieving reductions in the magnitudes required in the electric power sector is going to be a huge challenge. Both in the United States and worldwide, 2/3 of electricity generation still comes from burning coal, oil, and natural gas, virtually all of that without any capture of the carbon dioxide combustion product. 2 billion tons of carbon dioxide per year from fossil fuel power plants in the United States alone, 13 billion tons of carbon dioxide from fossil fuel power plants worldwide. I might add that over 70% of the global power sector total of greenhouse gas emissions is coming from coal-fired power plants. So what are our options? How do we achieve the deep cuts in greenhouse gas emission from the power sector that are needed? I'm sure everybody in this room knows the list. It's not actually all that long. Increased efficiency in electricity end use, more switching from coal to natural gas, improved fossil fuel power plants, most specifically with carbon capture, use, and storage, more renewables for electricity generation, particularly some of the non-hydro renewables such as wind and solar, more nuclear fission, and ultimately maybe nuclear fusion if we can make it practical and affordable. Now the key point is that all of these options have attractions and all of them have challenges, liabilities, shortcomings. But the point I really want to emphasize is that the litany of challenges that these options for reducing greenhouse gas emissions face is not a reason for taking any of them off the table. Given the importance, indeed the imperative, of electricity supply that is adequate, affordable, reliable, secure, and far more climate friendly than today's, the only sensible strategy is to do everything we reasonably can do through research and development, innovation, and public-private partnerships to master and overcome the challenges that each option presents. With this approach, I thought that was somebody protesting, but it's just a competing announcement. At least it's only in French. With this approach, we establish portfolio diversity as a hedge against inevitable uncertainty and surprises. And that precisely is President Obama's energy strategy. To meet the ambitious carbon reduction goals that are at the core of the COP21 negotiations and simultaneously meet the energy needs of a growing global population, we will need to embrace all of the tools in our toolkit. What today's panel highlighted so well is how ingenuity and innovation can contribute to addressing and overcoming the challenges that nuclear energy presents and unlocking its full potential. Through research and innovation, we can reduce capital cost, we can maximize safety against malfunction, mistakes, malevolence, and natural disasters. We can manage radioactive waste in ways that are not merely technically sound, but that can gain the confidence of the public. We can minimize the pathways by which nuclear energy could contribute to the proliferation of nuclear weapons. We can increase fuel utilization and improve electricity generation efficiencies with higher operating temperatures. And we can maximize reactor versatility to meet both on and off-grid electricity needs, improve load following to better pair nuclear energy with renewables, and meet a range of non-electric energy needs traditionally supported by fossil fuels, such as desalination, high-temperature industrial process heat, and hydrogen generation. In closing, let me just emphasize that nuclear energy, as has already been pointed out, currently provides 60% of non-fossil generation in the United States and 30% worldwide, and it operates at a 90% capacity factor. It is crucial to maintain this contribution of low-carbon power generation in the mix. But in addition, we now have the opportunity, with improvements in materials and technologies and through innovation, to make nuclear energy everything that it can be. Not least, we can make it an expanded contributor in both the United States and worldwide to minimizing the risks from climate change. Almost exactly 1 month ago, on November 6th, my office, OSTP, and DOE co-sponsored a nuclear energy summit in the White House, bringing together industry, academia, government, and civil society to talk about the potential for doing just that. And I am delighted that so many of the good points made there were made here again by this panel. So I thank the panel, and I thank the audience.